And hopefully this will, I don't know why I need my video considering I have a mask on, so that doesn't really do much for us anyway. Okay, so a couple of things before we begin. I was looking over your schedule last night, and I know you had something due yesterday, and you have something due today, and you have something due tomorrow. And your honor lock practice is due Monday. Now that's a 5-question. No, hint, hint. All the answers are true. So if you'll practice that, if you have never taken an exam through honor lock before, it can be a little persnickety. So it's a good idea to practice before you sit down to take an exam. So I would like for you to do that. If you need to practice a second time because the exam's not for another couple of weeks after you practice the first time, we can open that back up for practice again. It's just you need to practice. But anywho, you had a day 3 homework assignment was due on Tuesday, the 26th. And I didn't see any issue with pushing that out a day, which I did. As a matter of fact, I don't see any issue with doing this, which I need to fix in honor lock, my open math, sorry. And I can do that. Let's just push those out and I'll repost your calendar later this morning. Let's see, what do we have due? So the 27th, you had day 3 due. Let's just fix that and change that to Thursday. Give you a couple more days to do that and then just push the quiz out. You had a quiz due also. Let's push that out a day. How's that sound?
Thank you.
All right, and I will post the calendar update later this morning. All right. Are there any questions this morning? I do need to take roll, which I neglected to do on Tuesday. I'm terrible. If I don't do it at the beginning of class, I forget. And I will get that silly wrong class. I will get that silly seating chart, I promise, next Tuesday. Then I won't have to bug you. Alrighty. Carl. Sean. Okay, you're here. Kyra.
Here.
Kaylee.
Here.
Eric. And Alicia. Sadie.
Here.
Cooper. Jordan. Caitlin. Alexis.
Here.
Abby.
Here.
Peyton.
Here.
Cody.
Here.
Jared.
Here.
All right. It's been a morning. I got in my car to head out here for my 8 o'clock class. And there are 2 things I can drive in. I can drive in the fog and I can drive in the dark. I cannot drive in the dark when it's foggy. Can't do it. So and we live in the country. So I got a mile from my house, turned around and came back home. So I did my 8 o'clock class from home and then had to rush out here for this class. All right, where are we? We're finishing up chapter 1. We looked at sampling methods, did we not? We did. Looked at random number generators. Okay, so we're going to start our discussion of frequency tables this morning. And then we're going to spend a lot of time with frequency tables. Okay, who came in late? Sean? Who else?
I think yes, she's in.
Caitlin.
I think I said Carl, and that's because I don't have it. Carrie? Because I can't see. I'm old and blind. Hey. Frequency tables. No, you just walked in. I'll get you right now.
Thank you.
All right, I think we're good. Hey. So we, as I said, are going to start our discussion this morning of frequency tables. And we actually spend quite a bit of time on frequency tables, and they come up again later in our discussions of probability. So we're going to create and interpret frequency tables. I do have another calculator up here when we get to the calculator part if anybody needs it. Okay, so you've already done the assignment, hopefully, on rounding off. And hopefully you remembered how to round off from your previous math classes. Typically, in math and engineering, you round off to one more decimal place than your most accurate measurement. So for example, if the average of 3 quiz scores 4, 6, and 9 is 6.3, we round off to the 10th place because our scores are whole numbers. So that is a typical way to round off. Now, in my open math, they normally, I say typically, normally, most of the time, tell you how many decimal places to round off to. And usually it's 4 or 3. Sometimes they don't tell you. It's a safe bet if they don't tell you that rounding off to 4 places is sufficient. I haven't seen any of the problems in my open math where that's not the case. So if they don't tell you how much to round off, 4 decimal places is a safe bet, even though their data is not accurate to 3 decimal places, they have you round off to 4. And in most cases, if your answer is a fraction, you can leave it as a fraction. You don't have to change it to a decimal. If it counts it incorrect when you change it to a decimal, that's probably because it expected it to be a fraction. So if you come up with any of those scenarios and you're frustrated, let me know and I can help you out, giving you credit or telling you, yeah, you should have written that as fraction. Right. All right, we have 4 levels of measurement: the nominal scale, the ordinal scale, the interval scale, and the ratio scale. Not every statistical operation can be used with every set of data. Okay. And these are from the lowest scale to the highest. So the nominal scale is qualitative data that can't be ranked. For example, if we look at the color of everyone's mask, and we're in the 2021 where everybody wears masks. If we talk about the color of your mask, it doesn't make sense to say blue is better than black. I mean, you might think that, but it doesn't make sense to do that. So when you have qualitative data that you can't rank, that's not the nominal scale. The ordinal scale is also qualitative data, but you can rank it. And the most common example I think of when I think of the ordinal scale is surveys. I recently had a doctor's visit, and I think I told you about them bugging the BGBs out of me to fill out a survey. And their survey goes from completely unsatisfied to completely satisfied. And it was a 5 qualitative scale. But you can rank that because completely dissatisfied is worse than completely satisfied. So it's qualitative data, but it can be ranked. Now, the other thing about the ordinal scale is you can't actually measure a difference in the values. So if you have this good, satisfactory, unsatisfactory, you can't take unsatisfactory from good and get a value. So taking a difference in those values doesn't really make sense. Okay, so that's the nominal and the ordinal scale. So now let's get into our quantitative scales, interval and ratio. The interval scale is quantitative, but some things don't really make sense about it. Number one, 0 is kind of arbitrary. So an example of an interval scale is temperature. If we look at the centigrade versus Fahrenheit scales measures of temperature, 0 is kind of an arbitrary measurement, especially in Fahrenheit. At least in Celsius, they say 0 is what? The temperature that water freezes at. But in Fahrenheit, what's the temperature that water freezes at? 32. So what's 0? Cold, I guess. So it's difficult to assign an exact 0 value. And the other thing about 0 in the temperature scale is it's not absolute. There are temperatures below 0, correct? In both the centigrade and the Fahrenheit scale. The other thing about temperature scales is, what is it right now? It's 43 degrees according to my watch. Well, 66 or 86 degrees is not twice as warm as 43 degrees. So it doesn't make sense to look at the scale in that perspective. One temperature, 40 degrees is not twice as cold as 80 degrees. Okay, but 20 degrees is colder than 30 degrees. So the temperature rank actually makes a difference. Now, the last scale, which is the one that we prefer to use most often, is the ratio scale. It is quantitative data, and 0 has a value. So 0 makes sense. So if we were talking about the grade on your first exam, 0 would be that you get nothing right. And 100 is perfect. But if you score an 80 and you score 40, I'm just saying that just an example, 80 is twice as good as 40. You get twice as many problems correct if you score an 80 over a 40. So the ratios can be calculated, and differences also make, you can take the difference between numbers in the ratio scale. Okay. All right, so what's a frequency table? So here we have data on 20 students who were asked how many hours they worked per day. And these 20 students gave us values. Now, we did this the other day when we looked at rolling a die, and we let our calculators calculate random numbers from 1 to 6 20 times. So we've done this. We've created a frequency table already. So the students said that they had worked anywhere from, what's the lowest? 2. There's a 2 in there. What's the highest? To 6. So it looks like the students worked anywhere from 2 to 6 hours. So that's going to be our first column, our data values. So our first column is based on the actual data that we take. The second column is the frequency that that data value occurs, the number of times that it occurs. So if we look at 2 hours, we have 1, 2, 3. 3 students who said they worked 2 hours in a day. So the frequency of that data value is 3. If we look at 3, how many we got? 1, 2, 3, 4, 5. So 5 students said they worked 3 hours in a day. So the data value is 3, but the frequency at which it occurs is 5. We have 3 said they worked 4, 6 said they worked 5, 2 said they worked 6 hours, and 1 worked 7 hours. So the first column is always your data value. The second column is at what frequency that data value occurs, how many times it occurs. Okay, now another thing that you can do is you can calculate something that's called the relative frequency. That's the third column there. The relative frequency is the frequency of your data value divided by the total number of data values you have. So we had 20 students that we surveyed, right? So we had 3 students said they worked 2 hours a day. So the relative frequency is that frequency value divided by 20, or 0.15. And we frequently write these as percentages. So we could say 15% of the students said they worked 2 hours a day. 0.15 and 15% are the same thing. Or we could say, what, 25%. So that's a very typical thing for us to do in statistics, is to state the relative frequency of the occurrence of the data value as a percentage. Now, the other thing we might do is calculate a cumulative relative frequency. And this helps us to determine how many values are below a certain cumulative frequency. So the number of students who said they worked 2 hours a day was 3. The frequency was 0.15. So the cumulative relative frequency is 0.15. However, the next data value, 3, the frequency of that data value was 5. So the relative frequency was 0.25. If we add the first frequency, relative frequency, to the second relative frequency, we get 0.4. So the cumulative relative frequency of 3 is 0.4. What that says is 40% of the students said they worked 3 hours or less. To calculate the cumulative relative frequency of the data value 4, its relative frequency is 0.15. Add that to 0.4, you get 0.55. So 55% of them worked 4 hours or less, etc. Now the total cumulative frequency is 100%. So in our survey, 100% of our students said they worked 7 hours or less. Okay, now sometimes it makes sense to have our data values in ranges. This example represents a frequency table for the heights in inches of 100 male semi-professional soccer players. Now, if you have 100 male soccer players, what is going to be the range of their heights? Well, let's say we measure their heights to the nearest 1/10 of an inch. How many different heights can I get? A bunch of different heights. So their heights are not going to be all whole numbers. They're going to be a range of decimal numbers to 1 decimal place. So what we might want to do is categorize the data values in classes. So since their height was measured to the nearest 1/10 of an inch, we begin our classes at the nearest 100th of an inch. And maybe the shortest player, I don't know, is 60 inches. So we're going to start our classes at 59.95. So the shortest player is 60. We're measuring at the nearest 1/10 of an inch. So we begin the class at 100th of an inch. And we do that so that there is no one who's going to be outside of these classes. If we're measuring at the nearest 1/10 of an inch and we state the classes at the nearest 100th of an inch, everyone will begin at a class. Now you decide how many classes you want. In this example, they decided on what? 1, 2, 3, 4, 5, 6, 7, 8. They decided how many classes they want. You can determine the width of the class by a formula. So when you do this in your homework, it's got the formula. You take the upper class limit minus lower class limit and you divide it by the number of classes you want. So that gives us the width of each class. And then we just look at our data points. How many of these young men are between 59.95 inches and 61.95 inches? And you just count them up. Now, the lower class limit is the first number. The upper class limit is the second number. And you'll notice that the upper class limit of this class is the lower class limit of this class. So we've got the class width is what, 2? Is there 2 between 63.95 and 61.95? So we start at 61.95, we go to 63.95. So the next class begins at 63.95. All right, and then we just count the number of people who fit inside each of these classes. And you can calculate the relative frequency just like you did before. So we measure to the nearest 1/10. So our classes are to the nearest 100th. So if we had a player who's the shortest player was, let's say, 60 inches, our first class begins at 59.95. We decided how many classes we wanted. That tells us what the class width is. So what's the lower class limit to the upper class limit? Now we get to start having fun. Because we're going to do descriptive statistics. Let me open Excel. Oh, it's already open. Duh. Let me open my calculator. All right. Okay, we're going to start chapter 2 today on descriptive statistics. What we're going to do in chapter 2 is we're first going to look at graphs. And now I can't remember what homework section it is. It has the infamous box plot problem in your homework. When you get to it, you will recognize it. And I think it's in section 2.3, but I honestly can't remember because I did it yesterday and finally drew the box plot that my Open Math accepted my box plot because it's really hard to draw. So we'll talk about that when you get to it. If you cannot get your box plot to draw, I will give you credit for it. Trust me, I will, because it's hard to draw. And my Open Math is really hard to draw. Anyway, so we're going to look at stem plots, very easy to do. Histograms, which are pretty easy to do both on your calculator and Excel. And then we'll look at box plots. Box plots work really, really well on your calculator. They're not too bad on Excel either. They do pretty well in Excel. Then we'll talk about and describe and calculate the measures of locations. So we're going to look at quartiles. What's quarter mean? So if you have quartiles, it breaks your data up into quarters. And then we'll look at percentiles. Have you ever taken a standardized test? Haven't we all? Have you ever taken a standardized test where they give you your percentile? They say you ranked in the 90th percentile. We'll talk about those. Then we'll measure we'll calculate our measures of the center of data. It's called the measures of central tendency. We'll look at the mean, and you know how to calculate the mean. What's the mean? How do you calculate that? It's the average. We'll calculate the median. Well, you don't really calculate the median, you find it. The median means middle. And then we'll look at the mode. Then we'll talk about the measures of the spread of our data. This is actually an important thing to be able to calculate and recognize and interpret, because the spread of your data may have some important implications for you. So we'll calculate the standard deviation, and this book does, I think, they don't think they even show you how to calculate it by hand. It's not hard to calculate by hand. It's just a lot of work to calculate it by hand. So we're going to let our calculators and or Excel calculate the standard deviation for us. Okay, so in this chapter, we're going to look at numerical and graphical ways to describe and display our data. This is called descriptive statistics. So when you graph it or you calculate mean or standard deviation, you're doing descriptive statistics. Okay, so we're going to first look at stem and leaf graphs, which are called stem plots, line graphs, and bar graphs. And stem and leaf and line graphs and bar graphs are really pretty easy to do. Like I said, your calculator and or Excel do these very well. Okay, so we first need to talk about significant digits just for a second. So suppose you measure your weight to be 132 pounds on a scale that can read only to the nearest pound. My scale at home measures to the nearest hundredth of a pound. They've gotten fancier in the few years. So if you tell someone that you weigh 132.00 pounds, that's misleading. So if you add zeros to the right of a decimal place, you're misleading someone on the accuracy of your measurement. So as soon as you put those two zeros there, you're saying that you're accurate to the nearest hundredth of a place. That's not true. Your scale only measures to the nearest pound. So 132 and 132.00 do not mean the same thing. The digits in a number that represent actual measurements are called the significant digits. So in the original weight, 132 pounds, you have 3 significant digits. The 1, the 3, and the 2 are all significant. In this measurement here, what you wrote here, those 2 zeros are not significant because you're not measuring to the nearest hundredth of a pound. Oh, it helps if it's plugged in and stopped. Okay, so zeros are significant when they actually represent measurements. Otherwise, they're not. So we assume if it's written this way, that those 2 zeros are significant. Because why would you write them if they aren't? So if you see this measurement, you assume that when the person stepped on the scales, like mine that measures to the nearest hundredth of a pound, that they see 132.00. That's what they're seeing. So in this case, you can assume the zeros in 600 centimeters are not significant. So zeros that are to the right of a number that's not 0, but to the left of the decimal point are not considered significant. And they're not considered significant because you could write that in scientific notation, or you could write it in meters. 600 centimeters is 6 meters. So the zeros are no longer significant when you write it that way. Or if you write it in scientific notation, what is that in scientific notation? Is that 6 times 10 to the 2? So as soon as you write this as 6 times 10 to the 2, the zeros are no longer significant. So be careful with significant digits. The only subtlety in counting significant digits arise when we cannot be sure whether the zeros are truly significant. So if your teacher says there's 200 students in class, is that exactly 200 students or is that approximately 200 students? You don't know unless they tell you if those zeros are significant or not. So again, we try to avoid that ambiguity by writing the numbers in scientific notation when we can. Okay, so non-zero digits in a number are always significant. Zeros that follow a non-zero digit and lie to the right of the decimal point, such as 4.20 or 3.00, are always significant. If you write them there, then there's an assumption they're significant. I've been muted all this time. Well, that worked out really well. Zeros to the left of the first non-zero number, such as 0.006 or 0.00052, are never significant because you can write 0.006 or 0.00052 in scientific notation. Six times 10 to the what? Minus 3. So as soon as you write it in scientific notation, the zeros are no longer significant. And the zeros to the right of the last 0 digit, but before the decimal point, such as in 40,000 or 210, are not significant unless they're stated otherwise. Okay, so the stem plot is a quick way to graph data and gives an exact picture of the data. Because when you create a stem plot, you write down every single solitary data value. And so the problem with it is, if you've got 100 data values, it can take you a considerable amount of time to create a stem plot because you're actually writing down every data value. But you want to look for any overall pattern to your data. Do you remember the first day when we did the dot plot and we kind of looked for a pattern? These show up, do a very similar thing. They can actually show you a pattern in your data. Typically, you can see outliers. An outlier is a value that's extreme. It's either significantly below or significantly above your data values, so that you might have a problem. When you graph an outlier, it doesn't fit the pattern of your data. And outliers can be due to a lot of things, but if you have an outlier, you need to figure out why you have an outlier. Is it because of a bad measurement? Or is there something actually incorrect or wrong in the process? Okay, because you need to investigate. Every outlier that's in your data, you need to investigate. Okay, stem and leaf. Okay, so the number 23 has a stem of 2 and a leaf 3. So the 3 is our last significant digit, so it's going to be our leaf. And our stem is our first significant digit, so it's going to be 2. Now, if you have a number with 3 digits, the last significant digit, again, is our leaf, and the other significant digits are our stems. So for example, 5432, the 2 is our leaf, and the 543 is our stem. And you'll see what I mean by this in just a second. So the number 9.3, 3 is our last significant digit. So it's our leaf. Our stem would be the 9. So you write the stems in a column on the left-hand side. You draw a line, and then you list your leaves. Normally, we write our leaves in increasing order next to their corresponding stem. So our leaves should be in ascending order from smallest to largest. Okay, so here is an example. Can I move that? Get it out of the way. So here's an example of a stem and leaf graph. Now they don't have the vertical line, but they do have a space. So here on the left are our stems. Here on the right are our leaves. So the data values that are being represented by the stem and leaf plot are, the first data value is 33 or 3.3, depending on what your data is. Our second set of data values are what? 42, 49, and 49. Or 4.2, 4.9, 4.9. I don't think that they tell us if it's got decimals or not. So I'm going to assume they're whole numbers. So our third set of data would be what? 53, 55, 55. 61, 63, 67, 68, 68, 69, 69, etc. So you can see, if you look at this sideways, you can kind of see a pattern in your data. It looks fairly symmetric around what? The data values in the 60s. Okay, so how do you create one of these? For Susan Dean's spring pre-calculus class, scores for the first exam were as follows. And they did rank them for me from smallest to largest. Yay! Now, if they don't rank them for you, you can actually copy and paste the data in Excel and sort it, or you can just look at it, whatever works for you. So the smallest value is 33. The largest value is 100. Our last significant digit is in the ones place. So our leaves are going to consist of the one place, ones places of all of our numbers. The stems are going to be the other significant digits. So our stem is going to start at 3 and end at 10. Okay, now what are our leaves going to be? Well, our first data value is 33. So our stem is 3 and our leaf is 3. So that first row there represents the data value 33. Then what do we have? We have some 4s. 42, 49, and 49. So our leaves are going to be 2, 9, 9. And these should be in ascending order. Whoops, gave you the answer. Okay, and then what do we have? We have 53, 55, 55. Then we have some 60s. 1, 3, 7, 8, 8, 9, 9. Then some 70s. 2, 3, 4, 8. Some 80s. We got an 80, so we got a 0 there. 3, 8, 8, 8. And then 90, 0. 92, 94, 94, 94, 94. If I got 1, 2, 3, 4 of those, 1, 2, 3, 4 of those, and then 1 and 96, and then 100. And I tried to keep them in columns neatly because you can't see the pattern. When you type this into my Open Math, you can see the pattern quite easily. So let me erase what I've got, the mess I wrote here. So that we can see what this should look like. There it goes. Nice and pretty. So it looks like that most of the scores were from 60 to the high 90s. 8 out of the 31 scores, or approximately 26%, were 90 or better. But what the stem and leaf plot does is that it allows you to see the actual data. So I know there's a 72 on this exam. I know there's a 90, as a matter of fact, there's 1, 2, 3, 4 94s on this exam. Maybe this test is too easy, I don't know. Okay, now let's look at this one. We have the distances in kilometers from a home to a local supermarket. Create a stem leaf plot using the data. Now it looks like our last significant digit is in the 10th place. So our leaf is going to be the 10th place. And our stem is going to be our whole number. So we look like we start at 1 and end at what, 12? And I'm not gonna have room on my slide. My writing's too big. It would go down to 12. And then our first stem would be what? 1, 5, our first leaves, 1 and 5. And our second one, what, 3, 5, 7. So here's a pretty representation of it. And the other thing the stem and leaf plot does is looking at this data. All of our data is between 1.1 and 6.7, except for that 12.3. So looking at that 12.3, I'm thinking that might be an outlier. So is that outlier because someone truly lives that far from their supermarket, but this particular supermarket, but they just really like it. So maybe you just love Crest. So you drive all the way from El Reno to go to Crest because that's the best supermarket on the planet. Or maybe your odometer on your car is not working properly. So you'd have to investigate what that outlier means. Okay, line graphs. Another type of graph that's useful for specific data values is a line graph. So in this case, in a survey of 40 mothers, they were asked how many times per week a teenager must be reminded to do his or her chores. I like this example. I don't have teenagers anymore. The results are shown in the table. So if the number of times the teenager is reminded is 0, only 2 mothers said that. 5 mothers said they had to remind them 1 time a week. 8 mothers said they had to remind them twice. 14 mothers said 3. 7 mothers said 4, and 4 mothers said 5. So what you have here when you look at your frequency table, because that's what that is over there, you can create a set of ordered pairs from your frequency table, where the first column is the value on the horizontal axis, and the second value is the value on the vertical axis. So the first ordered pair would be 0, 2. So you would plot that 0 on the horizontal axis and 2 on the vertical. The second ordered pair would be 1, 5. So 1 on the horizontal, 5 on the vertical. 2, 8, 2 on the horizontal, 8 on the vertical. 3, 14, right there. 4, 7, 4 on the horizontal, 7 on the vertical. 5, 4, 5 on the horizontal, 4 on the vertical. And then you just connect the dots. And so what you can see from this line graph is you can easily see that peak, right? It just stands out. So what's the peak? 14. 14 moms said they had to remind their kids 3 times a week to do their chores. I mean, again, the frequency table tells us a lot, but what happens when we graph it? You immediately see the relationship, don't you? So that's what graphs are really, really good for. Okay, another type of graph is a bar graph. And this is what Excel does well. Excel is horrible at histograms. So what we do with Excel when we're drawing a histogram is we fudge it. Because it used to be really, really good at drawing histograms. Not so much anymore. Okay, so what we have here is data about Facebook. By the end of 2011, Facebook had over 146 million users in the United States. And so we have a frequency table here that shows the age group in the first column and the number of users in that age group and the proportion. So this column here is the relative frequency. So they took the 65 million and divided it by 146 million. and they get 45%. So this column, this proportion, is the relative frequency. 53 million divided by 146 million is 36%. 27.9 million divided by 146 million is 19 million. So then what they did is they created a bar chart. And each bar represents our age groups. And the height of the bar represents our relative frequency or our proportion. And typically we draw these in descending order just because it gives us a better look at the data. But you can just look at it, easily compare the age groups and the distance between, the heights of the bars, etc. Now, I would wager to guess. How about you? Now we are 10 years later. What do you think this looks like today? Would you guess this is the 45 to 64? No, you don't think so? I think most 13 to 25-year-olds are no longer using Facebook. What are you using? TikTok and all sorts of other stuff? But us old folks, we like Facebook. I have friends that I haven't seen since high school that we talk on Facebook all the time. It's kind of cool. I mean, I have a friend. She was my well, we went to college together, Sun College. She was my best friend in college, first 2 years, and she went to California. I stayed here. And we lost touch, but now I'm in touch with her again. Okay. Histograms, frequency polygons, and time series graphs. So a histogram, the difference between a histogram and a bar chart is that the histograms bars are contiguous. They touch each other. It has both a horizontal axis and a vertical axis. The horizontal axis is labeled with what the data represents. For instance, distance from home to school. The vertical axis is labeled either frequency or relative frequency or percent frequency or probability. So now there's your first indication of probability. A probability that something occurs is the relative frequency of that value occurring. That's what it is. So in those examples we looked at earlier, where we had 15%, that's the probability of that value occurring. And where are we? The histogram, like the stem plot, can give you the shape of the data, the center, and the spread. A rule of thumb is to use a histogram when the data set consists of 100 values or more. Okay, to construct a histogram, first decide how many bars you want. You make that decision. Now, telling Excel calls them bins, in case you're interested. The number of bars in Excel is the number of bins. You have to decide that. Those are called classes, which we saw at the end of chapter 1, and that represents the data. Many histograms consist of 5 to 15 bars or classes for clarity. The number of bars needs to be chosen. You have to make that decision. Choose a starting point for the first interval to be less than the smallest data value. So example was those basketball players when we had our shortest player was 60 inches. So we decided to start at 59.95 because we were measuring to the nearest tenth. So we did have players whose height was, 71.2 inches, that kind of thing. A convenient starting point is a lower value carried out to one more decimal place than the value with the most decimal places. For example, if the value with the most decimal places is 6.1, this is the smallest value, then a convenient starting point would be 6.1 minus 0.05 or 6.05. That would be a convenient starting place if your smallest data value is 6.1. If the value with the most decimal places is 2.23 and the lowest value is 1.5, then a convenient starting place would be 1.5 minus 0.005 or 1.495, etc. Now, the good thing about doing it this way is if you carry out the class limits, the boundary points, to one more decimal than any of your most accurate data, then you're not going to have any data points lie on a boundary. That's important. You need to be able to put all your data points in one of these classes. Okay, so here are basketball players. Our soccer players, sorry about that. Here are our soccer players. I guess 60 inches is kind of short for a basketball player these days, isn't it? What do you suppose the shortest player on the Thunder is right now? Probably about 6'3", yeah. And no, I never played basketball. It takes talent. Now, let's put it this way. It takes persistence, practice, and all those kind of things. And I didn't, and dedication. And I didn't have any of that. The following data are the heights in inches to the nearest half inch of 100 male semi-professional soccer players. Their heights are continuous data because it's a measurement, continuous quantitative data, since height is measured. And we're only measuring one thing, their height. That's it. You've got some problems that ask you, how many variables are you measuring? Only one, height. That's it. Okay? The smallest data value is 60. Since the data with the most decimal places has one decimal place, for instance, 61.5, we want our starting point to have two decimal places. Since the number 0.5, 0.005, 0.005 are convenient numbers, use 0.05 and subtract it from 60. So we start our first class at 59.95. The starting point is 59.95. The largest value is 74. So 74.05 would be where we end. So we're going to start our classes at 59.95 and end at 74.05. So then what you do is you decide how many bars do I want in my histogram? I want 8. And how arbitrary is that choice? Completely. You probably wouldn't want just 2. That wouldn't be real beneficial. And you probably wouldn't want 50. So 8 to 10 is a good place to start. So what you do is you take where your last class is going to end, which is the 74.05, minus where your first class starts, and you divide that by the number of bars you want. Then you take that number and round it up to your nearest whole number. Now, one of the problems I did in your homework the other day was this turned out to be 28. And you know what you did? You rounded it up. So whatever that number is, you round it up to the next whole number. Okay, so we're going to make each of our classes 2 units wide. So our first class is going to start at 59.95 and end at 61.95. point, then the next class is going to begin at 61.95 and end at 63.95. Okay, and then you count. So here are our classes, and then we just count the number of players that fit that class. So how many do I have between 59.95 and 61.95? 1, 2, 3, 4, 5. How many do I have between 61.95 and 63.95? 1, 2, 3. How many do I have between 63.95 and 65.95? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 15. And then you count how many are between the next two limits, the lower limit and the upper limit. Between 65.95 and 67, there are 40. 17 between the next two class limits, 12, 7, and 1. So now, once you have your classes and your frequency, now we have both the frequency and the relative frequency listed there. Now you're going to draw a graph, a histogram. And you don't actually draw these in my open math. They give you a choice and you pick which one's the correct choice. Okay, so what you do on the horizontal axis, you put your classes. So the first class starts at 59.95 and ends at 61.95, and the relative frequency was 0.05. So the height of our bar is 0.05. And you do the same thing with the rest of your classes. So just by looking at this, what do you see? You got any thoughts about what the shape of your histogram looks like? It looks very bell curvy, which is what you would expect for measurements of height. You would expect it to have that bell-shaped curve, which we'll talk about when we talk about the normal curve. What else do you see? Most of my soccer players are between 65.95 and 67.95 inches tall. That seems to be the sweet spot for semi-professional soccer players. I don't watch soccer all that often. Okay. Do you have a calculator? We're going to create a histogram on our calculator. And we're also going to do it in Excel. Okay, so what we're going to do is we're going to put this data in our lists. So what we have here is we have the number of books bought by 50 part-time college students at ABC College. So we have 1 book, 2 books, 3 books, 4 books, 5 books, or 6 books. For 1 book, we had how many students? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 students said they bought 1 book. 10 students said they bought 2 books. 16 students said they bought 3 books. 6 students said they bought 4. 5 said they bought 5 and 2 bought 6. Okay, so I'm going to go to my calculator. And I'm going to show you a couple of things. Now, the other day, we were playing with your calculators. We were doing random numbers and stuff. So you may have things in your lists. There are 2 ways you can clear out your lists. The first way is to go second plus. That's your memory. Number 4 is clear all lists. That will clear everything out of every list you have. If you don't want to do that, don't do that. You can clear out one list at a time also. So I'm going to exit out of here. So I'm going to do a second quit. I'm going to go to my stat menu. That's my statistics menu. And I'm going to go to number 1, edit. That's where I'm going to put my data in my lists. Now I've already put it in. If I wanted to clear this, which I don't, okay, I'm going to go to L3. So what I do is when I'm in that list, I arrow up where the list name is highlighted, and then I hit the clear button, and that will clear just that list out. Okay. All right, so I'm going to go back down, and I want you to put this in. In your L1 list, I want you to put the number of books, 1 through 6. So your first element in your first list is 1, second's 2. So you hit 1, enter 2, enter 3, enter 4, enter 5, enter 6, enter. Then you're going to arrow over to the second list, and you're going to type in 11. So 11 people said they had purchased 1 book, 10, 16, 6, 5, and 2. So when you get that done, okay, are y'all done? Okay, so I'm going to go to my stat plots. So I'm going to get out of here, second quit, and then I'm going to do second y equals, that's going to get me to my stat plots. Now I have plot 1 on because we were working with it the other day. If you don't have that plot on, we're going to hit enter, and you're going to select on and highlight that, and you're going to hit enter again, and that will turn that plot on. Now I'm on my TI-84 color, so I've got a bunch of graphs here, but I want the histogram, which is this bar looking thing. That's what I want. That's what I want highlighted. So I move over to that using my arrows, and I hit enter. Now, you've got 2 things that you have to tell your calculator. The X list is that first column. That's your data values, 1 through 6. The second number is the frequency. So you put the frequency of those data values in your L2 list. You can put it anywhere you want to. L2 is just convenient. So if you don't have L2 in your frequency, you're going to arrow down to that number, to that value. So just use your down arrow. And then you're going to tell it L2. So you're going to go second 2, and that's L2. Okay, so now you have all the information you need to draw your histogram. Now, if you let your calculator do its thing, it's not going to draw the histogram quite like you want it. So I could go zoom, stats number 9, and it draws a histogram. Now, what's the problem with this histogram? Well, it has some spaces here with no data. So I'm not real pleased with the way that histogram looks. So I'm going to go fix it. So I'm going to go to my window. See the window right there? All right, so my window is starting at 1 in the horizontal direction and ending at 6. So remember, if I drew a histogram, if my data is to the nearest whole number, I might want to start at a half instead of 1. So I'm going to start my window at a half. So I'm going to put 0.5 in. Now my last data value was 6, right? So I'm going to make my X max 6.5. Now my scale, here's where we get the thing to look the way we want it to look. So you remember, how did we figure out the number of classes we wanted, the number of bins? What did we do? We took the maximum minus the minimum and divided it by the number of bins we want. I want 6. I want 6 bars. That's what I want. So I can let my calculator calculate this. So what I do, I say 6.5, I'm using parentheses, minus a half. And I'm going to divide that by 6. That's how many bins I want. Now it turns out that my scale is going to be 1, but that's okay. But I'm going to take that maximum minus that minimum divided by the number of bars I want. I want 6. Okay. Now we can change our Y min and Y max. Did you see what happened when I clicked down? Did it do that calculation for me? Sweet. Sweet. Okay, let's change our minimum. I think they got -1. The minimum's not near as important as that X. What was the biggest number we had? 16. So let's make this 20. Okay, and now let's graph it. Hit the graph button. So you can tell your calculator how many bars you want. Do I have time to do Excel? Probably don't have time to do Excel. We probably will pick this up on Tuesday. We'll pop into Excel and show you how to do this in Excel. Are there any questions? Those of you who came in a few minutes late, what did I do homework-wise? Did I push a couple of homework assignments out? And you saw me do it, right? You gotta keep me honest. So what I did, because we haven't quite finished 2.2, I went ahead and pushed out the day 3 homework from Monday to Thursday, no, Tuesday to Thursday, and the quiz 2 from Thursday to Friday. Does that work for you? All right, we'll see you next Tuesday. Have a great rest of your week.